chemical reaction.
Hi everyone, the topic we are given is the rate of chemical reaction. Content, rate of chemical reaction, and the factors that affect rate. Rate of chemical reaction. The rate of chemical reaction is the change in the concentration of reactants per unit time. Chemical reactions occur at different rates. In addition, the same reaction can proceed quickly under some conditions. For example, at elevated temperature and slowly under others, for example, upon cooling. Moreover, the difference in the speed of some reactions can be very large. It is divided into homogeneous and heterogeneous systems. The rate of homogeneous reaction is the amount of substance that reacts or is formed during a reaction per unit time per unit volume of the system. The rate of heterogeneous reaction is the amount of substance that reacts or is formed during a reaction per unit time per unit surface area of the phases. And factors that affect rate: reactants concentration, physical state of the reactants and the surface area, temperature, pressure, and the presence of a catalyst.
Reactant concentration. Increasing the concentration of one or more reactant will often increase the rate of reaction. This occurs because a higher concentration of a reactant will lead to more collisions of that reactant in a specific time period. Here we have a few molecules that are few collisions and the rate of reaction is low. If we increase the concentration, we have many molecules that have more collisions and the rate of reaction is great. Physical state of reactant and surface area. If reactant molecules exist in a different phases as in a heterogeneous mixture, the rate of reaction will be limited by the surface area of the phases that are in contact. For example, if a solid metal reactant and gas reactant are mixed, only the molecules present on the surface of the metal are able to collide with the gas molecules. Therefore, increasing the surface area of the metal by bonding it flat or cutting it into many pieces will increase its reaction rate. Temperature. The higher the temperature, the faster the reaction occurs. For example, copper oxide reacts very slowly with diluent sulfuric acid, and when heated the reaction rate increases markedly, as evidenced by the dissolution of black copper oxide in the acid store from blue solutions. Pressure. Pressure increases the gas's concentration, resulting in the increases of the rate of reaction. The increases in the pressure on a reaction involves the reactant gases increasing the rate of reaction, and modifying the pressure on a reaction involving solids or liquids only has an effect on the reactant's rate. For example, in the case of manufacturing ammonia using the Haber process, the reactance rate between nitrogen and hydrogen increases using very high pressures.
Presence of a catalyst. A catalyst is a substance that accelerates a reaction by participation in it without being consumed. Catalysts provide an alternate reaction pathway to obtain product. For example, when potassium chloride is heated, it readily decomposes to give thioxygen. The decomposition occurs at high temperature. When manganese dioxide is added, decomposition takes place at lower temperature and a much faster rate. The catalyst manganese dioxide thus accelerates the chemical reaction while itself remaining unchanged throughout the reaction. Here, manganese dioxide acts a catalyst. Our lecture is over. Thank you for your attention.
Laboratory work. Rate of chemical reactions.
Experiment number 1, dependence of the reaction rate on the nature of the reactant. Pour a solution of hydrochloric acid into one test tube. And the same amount of acetic acid into the other. At the same time, we place a zinc granule in them. In a test tube with acetic acid, hydrogen gas is released at low rate. This can be explained by the fact that acetic acid has less acidic properties compared to hydrochloric acid.
Experiment number 2 depends on the reaction rate on the surface area of contact of the reactants. Pour approximately 2 ml of copper sulfate solution into 2 test tubes. At the same time, place a piece of iron wire in one test tube and the iron powder in the second test tube. The occurrence of a substitution reaction between copper sulfate and iron can be judged by the release of the red-brown substance copper from the solution. Sinks of the reaction operate faster in a test tube with iron powder. Since iron powder has a large surface area of contact with the copper sulfate solution, we see that grinded a substance leads to an increase in the reaction rate.
Experiment number 3. Dependence of the reaction rate on the concentration of starting substances. Place 2 zinc granules into test tubes and carefully pour acetic acid solutions into the first test tube 9% vinegar and into the second 17% acids. The reaction proceeds faster in the test tube in which the concentration of acetic acids is higher. Experiment number 4. Dependence of reaction rate on temperature. Place copper oxide in a test tube and pour dilute sulfuric acid into it. Copper oxide reacts very slowly with dilute sulfuric acid. Heat the solution to increase the reaction rate. After heating, we notice the formation of a blue solution due to the dissolution of black copper oxide.
Experiment number 5. Dependence of the reaction rate on the participation of the catalyst. Pour a 3% hydrogen peroxide solution into the bottom of the glass. Hydrogen peroxide is a very fragile substance and easily decomposes into water and oxygen. Under normal conditions, the decomposition reaction of hydrogen peroxide proceeds slowly. We do not observe any signs of the reaction, that is the release of gas bubbles. Therefore, add a little black manganese oxide powder to a glass of hydrogen peroxide and observe the intense release of gas bubbles. Then we bring a smoldering splinter into the glass. It flares up, therefore the gas released is oxygen. Manganese oxide is a catalyst for the decomposition of hydrogen peroxide. The catalyst participating in the reactions accelerates it but is not consumed in it.